All right, so here's what I want you to do. Exercise 1 says graph 2 to the x power. It's a review of what we did last time, learning our new exponential function. And if you wouldn't mind, after you've done that, just right off on the side here, write down what the domain and the range of the exponential function is. So I'm going to give you 2 minutes or so to do that, and then we'll check in. So if you're watching on the video, I'm going to pause the video so you can do the same thing. Okay, so for my exponential function, here's how it rolls. I'm just going to take my different x values. I'm going to put them in the exponent. And so the ones that we used, if you drew out the table, that's great. I'm just going to go from memory. So when I put in 3, 2 to the third power is 8. I'm going to make a nice dot right there at 3, 8. When I put in 2, 2 to the second power is 4. I'm going to put a nice dot at 2, 4. When I put in 1, 2 to the first is 2, so a dot right there. 0, 2 to the 0 is 1. When I put in -1, I get a half. That's as far as I'm going to go, just because I'm not a great artist anyway. And so here is your drawing of 2 to the x. That is fully review of what we did in class last time. We introduced the exponential function, and we got used to graphing it. We also noticed that the domain and the range of the exponential function, the domain, I can plug in any x values. You can see that that graph is going to go left to right forever and ever. So the domain is -infinity to +infinity. And then the range, the basic exponential function does not go below the x-axis. So 0 is the lower bound. And then infinity, you can see clearly it goes up really fast. And so also this is never going to go through the x-axis. So I'm going to put a parenthesis over there. So that is a review assignment. So if you have not done the homework from section 6.2, that is the essence of where we started. So now what we're going to do, because this was my promise to you at the end of last class, is this section here is going to fuse together what we did in section 6.1, talking about inverses and how to find inverses with these exponential graphs. So in order to review that, I have exercise 2 for you. Now, before you do exercise 2, because I know it's been a long time, we had spring break, or maybe you watched the video after spring break, we are going to use the points in this graph we just did to graph the inverse of the exponential function. Okay. Well, what is the inverse? How do I create the inverse? What do I do? Flip the x and the y. Right, we did this for other graphs in class and on the video. So what I want you to do, I'm going to give you 90 seconds. I want you to flip the x's and the y's of that, and then I want you to graph the result, please. And then underneath that, hypothesize what you think the domain and the range of this inverse graph are. All right, so the inverse, all you do to get the inverse is you flip-flop the x and the y values. Okay, that's all the inverse is. So this first point, I'm just going to go from the right side of this graph to the left side of this graph. This first point right here is the point 3, 8. So when I flip the values, I have 8, 3. So I'm going to go 5, 6, 7, 8, and 3. So there is my inverse point of that one. This is the point 2, 4. When I reverse them, it becomes 4, 2. So I'll put that right there. This is 1, 2. So when I reverse it, it becomes 2, 1. This is 0, 1. So when I reverse it, it's 1, 0. And last but not least, I have -1 and a half. So I'm going to go over half and down 1. And so there are my points that form the inverse. And so the inverse graph is going to look something like this. And just as the x-axis is the asymptote of the original graph, when I flip it, the y-axis is going to be the asymptote of the inverse graph. So this right here, this is the inverse of the exponential. So this is the inverse of 2 to the x power. It's what I get when I flip-flop the x and the y's. That's what the graph looks like. So when I go over to my, one other thing about the inverse we saw when we were together last time, a function and its inverse are symmetric. Does anyone remember what line a function and its inverse are symmetric around? Did you do that? Okay, I'm going to give you credit for that. That's as close as anybody else came. So it's the line y equals x. So I'm just going to put some dots in pencil here. This is the line y equals x. That is, I'm just going to make a dotted line here. Any function and its inverse are symmetric. They should be the exact same thing on both sides of the line y equals x. Meaning, if I take my paper and I fold it diagonally along that line y equals x, the two graphs are going to match up perfectly. Okay, that's what it means to be symmetric about that line. Again, we broached all this when we talked about inverses. So if you've not watched that video, if you've not gone through the worksheet, please do. Okay, there's lots of stuff there that it's going to be on the test. So now, what's the domain of the inverse? Well, I can see here that the lowest x value is going to be 0, and this goes to the right very fast, so it goes to infinity. And then the range of the inverse, it's going to go down really fast forever and ever, and it goes up slow, but it's eventually going to get to infinity. Another thing we said about a function and its inverse, since I'm flipping the x's and the y's to get the inverse, I just flip the domain and the range. So we can see the domain of the original function was -infinity to infinity. So the range of the inverse is -infinity to infinity. The x's become the y's and vice versa. The y's become the x's. That's what it means to be the inverse. Okay. So that kind of catches us up to the real quick review of what we did in section 6.1 and 6.2. So another section 6.1 comment, piece of content is this. Example 1, I'm going to work this one with you. Okay, we're going to find the inverse of 2 to the x power. Okay, we talked about finding the inverse of something analytically. Okay, and here was the process. I'm just going to go through those exact same steps that we went through last time. Okay, so we are going to now here come up with the function, the equation that matches or that defines this red graph. That is my goal here. Okay, well, let's do that. So the first step, does anyone remember the first step when it comes to finding the inverse? That's the second step. So you're just one step ahead of me. The first step, though, before I can switch the x and the y's, I've got to have a y. So the first step is purely notational. I'm going to change the f of x into a y. And then, yes, exactly what I was told. Let's find the inverse. This here, in any problem you do analytically, this is the inverse step. I'm going to flip-flop the x and the y. So I'm going to put the x over here, and I'm going to put the y in the power. Okay. This right here, this is the inverse. That is the relationship that defines that red graph. But here is the problem. Not so much a problem, it's just a notational thing. This isn't solved for y. Every function that we have used this whole semester, every function you will ever use is solved for y. We have no tools to solve this for y. We don't know what to do when there's a variable in the power. So remember, the next step in any finding the inverse is you've got to solve this for y. I'm just rewriting the steps that I wrote out when we were together for section 6.1. So here is where we get a definition. We're going to come back. We're going to finish this in a minute. Okay. So this is the new bit of information. This is what we're going to practice for the rest of today, is this definition right here. Okay, so this is super important. This is probably brand new for most of you. This is called the logarithm. And so the definition of the logarithm says this. Okay, if I have an equation that is x is equal to some number to the y, this is my exponential statement. Just to refresh your memory, because I know a lot happens between times we're in class together, we said last time that in our exponential statement, we're only considering values of a that are greater than 0. We're not considering any negatives. And also a is not going to be equal to 1. Okay, so that still applies to this situation right here. So if I have an exponential statement, this is just a definition, okay? This is purely notation that we're going to get used to. This is exactly the same thing as this. Y is equal to, so now I have it in a format that I like. It's y equals what's called the logarithm, which is abbreviated log, L-O-G, the logarithm, base A of x. So again, because I don't assume, maybe you have seen this before, but I make no assumptions that you have. Okay, we're going to practice this definition. Two things that I want you to notice. This right here is the base. It's the base of the logarithm. It's the base of the exponential. It's the same thing. And then the thing that you should recite to yourself, if you haven't seen this before, is my logarithm is always equal to the power. Logarithm equals the power. Basically, what this gives you is what power of the base gives you whatever value you're taking the logarithm of. Okay, so we'll do that. So now I can finish off my finding the inverse. We just defined it. So here I'm solving for y. I'm using the definition that we just had. So the power, the y, is equal to log base 2 of x. And then the last step in any find the inverse analytically problem is just notational, like the first step. Instead of having y equals, I'm going to let everyone know this is a function. I'm going to let everyone know the relationship to the original thing. And I'm going to write this f with a little negative 1. Remember, that's not a power. That's just the notation for the inverse. Log base 2 of x. Okay, so we are going to practice that definition that's down at the bottom of the page, the equivalence between my exponential statement and my logarithm statement. So if you need to, keep your thumb on that problem. We're going to flip the page. I've got an example that I'm going to do, and then I got a bunch of examples that you're going to do. Okay, so example 2, this is my example. Okay, the purpose of pretty much every problem on this page that we have is just practicing this definition. Okay, because I want to get this into your brain because this is important for the rest of this unit. Okay, and if you go on to pre-calculus after this, if that's your math destiny, you're going to use logarithms a lot. Okay, if you're going to take calculus because you're going into some field related to calculus, you're going to use logarithms a lot. Okay, so here goes. This is a statement I think we'd all agree with. 5 to the third is 125. It's just some arithmetic. So what we're going to do is we're going to rewrite that as a logarithmic statement. So here we go. I've got the logarithm. What's the base of the logarithm going to be, would you say? 5. It's the same as the base of the exponential statement. It's 5. So I'm going to make a little subscript right there. That's a small 5. Now, when I was first learning it, here's how I did this. Okay, you don't have to do it like I did. I'm just telling you what my brain did. So I have the log. That's the base. The logarithm is always equal to what? Power. So what's the power? Okay, I'm going to put the 3 over there, and then the odd man out or the odd thing out here is that 125. So there we go. So this says log base 5 of 125 is 3. It's just a different way of looking at an exponential statement. This says what exponent of 5 gives you 125? Well, that's 3. The logarithm always produces a power. Okay, so what I would like you to do is we're going to go one at a time just to practice. If you have any questions, I understand this is goofy and different and weird. Go ahead and do exercise 3, please. In exercise 3, here's what I'm hoping you wrote down. I've got the logarithm. What's the base of this logarithm going to be? 2. Excellent. I'm going to skip the next part, and then the logarithm always produces a what? The power. So the power is going to be 6. So it's log base 2 of 64. That's the only other number left. Log base 2 of 64 equals 6. So far, so good? All right, we're continuing our practice. Do exercise 4, please. Okay, so this problem, I just gave letters because I want to make sure that we can do this whether we're familiar with the arithmetic or not. So I have log, what's the base of this logarithm? The m, yes, equals, the logarithm always produces a power, so what's the power? N, and so then the other thing is just what I'm taking the log of. Log base m of t equals n. The next few problems, we're just going to do the reverse. Okay, because the logarithm definition goes both ways, left and right. So here we go. I've got log base 6 of 36 equals 2. So we're going to convert this into an exponential statement. It's going to be handy to be able to do this depending on what problem we're going to do as we go forward. So what's the base of this logarithm? 6. What's the power? Is equal to the other number, which is 36. Great. Do the same thing for exercise 5, please. Okay, what's the base of exercise 5? 7. What's the exponent? 0. And then the other number is 1. Fantastic. All right, one more of these. Exercise 6. What's the base of this? B. What's the exponent? Is equal to the other number, which is r. B to the t powers r. We doing all right? We catching on to this definition? Okay. The next 4 problems, again, we're just practicing the definition just in the context of another problem. So the next one I'm going to do with you, it says, let's solve this. Okay, we can sure do this. So x is equal to log base 8 of 4. So the way that I'm going to solve any of these logarithmic statements is I'm going to convert them to exponential because we've used it for so long, we probably naturally think better in terms of exponentials. So here we go. I've got 8, which is my base. What's the exponent? X is equal to 4. Now, the reason I gave this problem and the reason there'll be one on here like this for you is this just reminds us how to solve an exponential equation. Okay, we talked about that last time. And I'm just going to equate the bases. What base can I use to write both 8 and 4? 2. Yep. 8 is 2 to the 3rd. 4 is 2 to the 2nd. So on the left, 2 to the 3rd raised to the x power, that's 2 to the 3x power. On the right, 2 to the 2nd is 2 to the 2nd. And I mentioned this over and over last time that this is the exponential function is a one-to-one function. So that means if these two things are equal, that means the exponents have to be equal. So that's how I can make this statement, 3x has to equal 2. And when I divide both sides by 3, I get that the x value is 2/3. So just combining there our new thing with the definition with something we did last time to make sure it stays fresh. So what I would like you to do is exercise 8. Use the definition to solve exercise 8. Okay, so I'm going to use the definition. So this is the new bit right here. What's the base of this statement? 4. What's the exponent of this statement? 3 over 2, excellent, equals x. So it's kind of already solved. Your calculator can tell you that, or you can use properties of exponents. If you remember, when you have a fraction in your exponent, the denominator becomes your index of your radical. So what this is the square root of 4 raised to the third. Square root of 4 is 2. And so 2 to the third becomes 8. So that is my answer to this problem, 8. Again, I'm fine if you use a calculator to do that, but properties of exponents just gave me the same thing right there. Do exercise 7 using the definition to solve that logarithmic equation. Right, what's the base of this logarithm? X. The exponent is 4, and that equals, all right, great. That's the new bit. Okay, if you're doing that, then you've got the definition. The rest of this is stuff we've encountered at one point or another. What am I going to do to both sides of this to solve this for x? If I have x to the 4th power is 16, I'm going to take the 4th root. Yes. So I'm going to take the 4th root of x to the 4th, and I'm going to take the 4th root of 16. And so the 4th root of x to the 4th is x. Here's the thing to remember. I know there's a bunch of details, and I get it. Math gets like that sometimes. When you take the even index, like a square root or a 4th root of a number, you actually get 2 answers. You get a positive answer and a negative answer. And the 4th root of 16 is 2. But even if you didn't do that, you might have got this accidentally right, because if you remember, x is the base, and we're, by definition, there's no negative bases. Okay, so we're going to throw that one out because it's not part of how we defined the logarithm. I did that on page 1 when we defined this relationship. None of the bases will ever be negative in the problems we're considering. So the only answer that matters here is 2. All right, one more problem you're going to go ahead and solve for me. Exercise 9. If you have any questions about this at all, please ask them. There are no bad questions about this. This is tough stuff. All right, so one more time, what's the base? 2, perfect. And what's the exponent? 3, and that equals, great, the x plus 1. Well, this one's a little easier to solve than all the others. 2 to the third is 8. And then I'm going to subtract the 1 from both sides, and I get that the answer to this is 7. So there is my solution. Okay, again, the new part of what we're doing is the rewriting logarithms as exponentials and vice versa. And each of those problems after that, the way we solved it was something that hopefully is in our memory banks somewhere. At the bottom of this page, as we're getting to know this thing called the logarithm, there are 2 bases that get used more often than almost all the others. Whether it's an application in a economics class or biology or physics or calculus, wherever, there's 2 bases you'll see more often than anything else. The first one's called the common logarithm. The common logarithm is based on the fact that we use a base 10 number system. And so log base 10 is called the common logarithm. And because it's so common, because it's used so frequently, math people are fundamentally lazy people. And so math people don't tend to write the 10 there. So if you see just a log without a base, okay, the base is assumed. Let me raise that up. Sorry, I didn't mean for it to be so low. When you see an log without a base, the base is assumed to be 10. Okay, so you can take that to the bank. So on your calculator, unless you're using, I don't know about the Android phones, unless you're using the calculator in the Apple, all your calculators are just going to have log without a base. That's base 10. On the Apple calculator, they actually put the little 10 on there just so that you know for sure. The other one that is used a lot is another different base. This is called the natural logarithm. It's the log, the logarithm, and this number is an irrational number like pi. Irrational numbers, remember, if you've ever known this, are numbers that don't repeat and don't terminate as decimals. So pi never ends and it never repeats. This is the number e. So if you have log base e of x, then that's called the natural logarithm. And the way that would get written is ln from French, logarithme naturel. So that's how the abbreviation goes. So on your calculators, again, if you see the ln, that's the natural logarithm. Personally, in this class, I am not going to do too awfully much with the natural log, the base e, because that's kind of a pre-calculus concept of where that comes from. E is approximately equal to, if you're curious, E is approximately equal to 2.71828, and then it goes on forever in kind of a random assortment of digits. So you will have some problems in the book that are on your homework that'll involve the natural logarithm, but for no other reason than it obeys all the same properties of any other logarithms. So I will, on your test, I favor just using common logarithms because you have more experience with that, and we haven't really talked about where E comes from all of a sudden. It just kind of pops up in this class. All right, so I'm going to flip the page. Now that we know a little bit about logarithms, we know very little bit, we can talk about some of the properties of logarithms. Now, the thing about the properties of logarithms is I've said a bunch of times, I'm going to say a bunch more times, the logarithm produces a what? Power, yes, almost everybody almost forgot. That's okay. We're gonna get that into your brain. The logarithm produces a power, so a lot of these properties of logarithms are based on properties of exponents. So we're just going to go through kind of the 6 most popular properties that you will see as you're going through this class. So the first one is the log base a of 1 is equal to. So basically, if you're taking the logarithm of 1, what power does that produce? Now, you don't have to write this down if you don't want to. I'm just going to come over here to the middle and show you why this is true, not just what it is. So if I have the log base a of 1 is equal to, I don't know, I'm going to put a question mark there. I don't know what it is. Well, now I'm just going to use the definition like we've been doing. So I've got a to the question mark power is equal to 1. And what power do I raise anything to that produces 1? 0, yes. So whenever you take the logarithm of 1, the power that is related to it. Again, all these are based on the rules for exponents. The power that I raise anything to get 1 is 0. The next two properties are based on the fact that the logarithm and the exponential, we already saw, are inverses. That's our whole reason for discussing logarithms and bringing them up in the first place. Okay, is that these two things are inverses. And again, I don't know if you remember this. It was a little while ago. It was before we took our break. But when I compose a function and its inverse, when I put them together, it always produces what you started with. You always get back what you started with. So if I have the log base a of a to the k power, so I have the logarithm base a, I have the exponential base a, then what that's going to equal is just the power k. Because they undo each other. The exponential and the logarithm undo each other. It's like tying your shoes, then untying your shoes. You're back where you started. Same thing here. I've got the exponential base a, and then I've got log base a. So again, I'm tying my shoes, then I'm untying my shoes. They undo each other, and I'm left with k. Now, those aren't super interesting properties. The next three are the ones that you're going to use more often than not. Product rule, quotient rule, power rule, again, based on the properties of exponents. So the product rule says this: if I have the log base a of a product of two things, well, again, remind me, what do you do with the powers when you multiply your bases? You add. Okay, so that's just based on this. So when you see that you have a product in here, then what you do is you can separate these two things. You can say, okay, that's the log base a of x plus the log base a of y. I'm adding the powers. Let me just, as an aside, tell you a tragic math error that I never want you to make, please. If I have the log base a of I'm adding two things together, there's nothing you can do with that. Okay, but a common mistake students want to make because you see these other properties is you want to say, oh, cool, what I can just do is distribute the logarithm and have log base a of x plus log base a of y. That is wrong. Don't do that. You cannot distribute. This is not a multiplication problem. Okay, so don't distribute. Okay, the only time you can separate what's in here is if it's either multiplication or like the next problem when we have division in the parentheses. If it's addition, you can't do anything. So when I have the logarithm of a product, I have the log base a of x plus log base a of y. Great. All right, well then let's say the quotient rule, log base a, and I have x divided by y now. Yeah, so we're just going back to the rules for exponents. Okay, when I divide by bases, what do I do with the powers? Subtract them. Great, I've already heard that, and I heard it again. So I have the log base a of x minus the log base a of y. The numerator comes first, the denominator second. Again, all of these things are based on the properties of exponents because logarithms produce exponents. They produce the power. The last one is the power rule. Remember, the power rule says if you have a power raised to a power, so that means I have the log base a of x, and then I'm going to raise that to some power n. I don't remember what letter our book uses, so I'm going to use n for number. Well, when you have a power raised to another power, so I've got my logarithm raised to another power, what do you do with the exponents in that situation? You multiply. So I'm going to take that n, and I'm going to put it out front, and it becomes n times the log base a of x. Again, based on the properties of exponents. All right, I know that's a lot. That's a big chunk of information. You've been given the definition of a logarithm. That's big enough for the day. And now you've got these properties. So the rest of our time together today is just going to be, or actually, I thought there were 4 pages. There's only 3. The rest of our time today is just going to be practicing these properties. And if we have time left over, which we might, then I'll just make up a couple more problems because this is big stuff and I don't want to let you out early without maximizing our time together. So this problem right here, example 5, I'm going to work this with you. All we're going to do, okay, sometimes it's going to be handy to use the properties to expand things. Sometimes it's going to be handy to use the properties to contract them back together. It depends on what you're doing. Okay, and that's what we're going to talk about when we come back next time. So what we're going to do in example 5 is we're going to take this and we're going to expand it using the properties of logarithms. So the first thing I notice is I've got a quotient. I'm going to start with that. So the first thing that I'm going to do is I'm going to use the quotient rule, which says when you have a division, then you subtract the exponents. So I'm going to have the log base a of what's in the top, x squared y. And then I'm going to subtract the log base a of what's in the bottom, which is z to the third. Okay, so top minus bottom. Second thing I'm going to do is I notice I've got a product in this first logarithm, so I'm going to use the product rule. Product rule says when you're multiplying what you do is you add the powers. So I'm going to add. So I'm going to take log base a of x squared plus log base a of y minus log base a of z to the third. And the last thing I'm going to do, so I incorporated every one of the properties into this first example just so that you'd feel really excited about it. And so now I'm going to use the power rule. So I've got these things to the power. According to the power rule, I can take whatever that exponent is and I can just bring it out front. Okay, we multiply the exponents. So here we go. My first term is going to be 2 times the log base a of x. That's done. The next one doesn't have an exponent, so it's going to stay the log base a of y. And then minus 3 log base a of z. All right, so the next one I would like you to do is actually right below that. That's the first of our exercises we're going to do. So exercise 10, I want you to please take that logarithm. I'm going to give you a couple minutes, and I want you to use those properties to split it apart. All right, so I'm going to get started. If you got any questions, let me know. So again, I've got a quotient. I'm going to start with that quotient right there, and I'm going to break that fraction apart. So again, my quotient rule is I subtract my exponents. So I have the log base a of the thing in the top, which is x to the 4th, minus the log base a of that thing in the bottom, which is y squared times z to the 5th. You did that, you're off to a good start. Okay. And on the test, do as much as you can. I'm hoping you can do the whole thing, but even if you can just do that quotient rule right there, you get partial credit. Okay, so always do as much as you can when you're doing the problems on the test. Okay, now here's one little thing. I made yours a little bit different than mine because you have this product that's after the minus sign. Okay, I did that on purpose just to remind us of this thing. Don't forget that you have to always distribute. I'm subtracting everything that comes next. So when I do this product rule, I've got log base a of x to the 4th minus. Now I'm going to break this logarithm into two things. So I'm going to put some parentheses, and I've got log base a of y squared plus log base a of z to the 5th. Now, if you didn't need the parentheses and you knew that you were going to have to apply this minus sign to both these terms, that's fine. I have no problem with that. You can see that both of these terms here are in the denominator, so that's why they're both going to have a minus sign. And what I'm going to do last is I'm going to distribute that minus sign, and I'm also going to apply the power rule at the same time. So in the first term, this 4 should come out front. So I have 4 log base a of x, and then a minus, and then I'm going to bring down the 2, so minus 2 log base a of y. Then I'm going to distribute the minus, and I've got the 5, so minus 5 log base a of z. And there's your properties of exponents. Before we move on to the next problem, does anyone have a question, comment, concern, something you're just not quite seeing? Logarithms are tough. Make no mistake. I understand. All right, then exercise 11. I'm going to give you a little hint on exercise 11. Before you do anything, this cube root of a squared, you should rewrite this term right here. You should rewrite this as with an exponent instead of a radical. Okay, so use your properties of exponents and rewrite that as a to some power, and then you'll be able to apply 2 of the properties of exponents. All right, so let's see how you did. I know it's a tough problem. I'm bringing back a lot of prior knowledge that maybe wasn't too secure in your brain anyway. So I gave you the hint of we need to write this as an exponent. So I've logged the base a of what is the power that I'm going to put on this a? Yes, 2/3. The index of the radical always becomes the denominator of the fractional exponent. Okay, so I told you there was going to be 2 properties of exponents, two properties of logarithms that you could apply to this. The first one is the power rule. I've got that 2/3 power, so I'm going to bring that down to the front. So I've got 2/3 log base a of a. And then the other property, maybe you didn't quite see it, but the other property is going to be this one right here, the fact that the logarithm and the exponential, they are inverses. Okay, and you're just going to, when you have the logarithm and the base of what you're taking the logarithm are the same, then the result is just going to be the power. So what is the power on this a right now? I took the 2/3 down to the front. So it's just 1. So this, since it's the logarithm base a and it's a, these two things, they undo each other, they cancel each other out. And so that's just going to leave me with 2/3. Okay, so I'm going to make a little note because I know that that's tough. We're just learning this. These two things are inverses because the bases are the same. What I'd like you to do with exercise 12. Exercise 12, I've given you an expanded logarithm, and I would just like you to do the reverse process. So first thing I would recommend is do the power rule and get any coefficients up, and then just you're reversing it and you're using the product rule and quotient rule from there. And give it a try, do your best. We'll compare notes in a minute. So I'm just going to get started. If you're still working, keep working. The first thing I'm going to do is I've got this 4 right here, this coefficient. So I'm going to use the power rule for that. So I've got the log base 3 of x plus 2, and that, leave that the way it is, plus the log base 3 of x to the 4th power minus log base 3 of 2. Okay, so there's the first property of exponents that I've used. And now I'm just going to work left to right. Okay, I'm going to do one thing at a time because I don't like to do too much. So I'm going to first use this one right here. I notice there's a plus between those two logarithms. So that means this is going to be the product rule. I multiply, when I add my powers, I'm multiplying. So I've got log base 3 of x to the 4th times x plus 2, and then minus log the base 3 of 2. And now lastly, I've got this minus sign. When I subtract the powers, that means that I'm dividing. So I've got log base 3, and then I've got all of this junk is what I'm taking the logarithm of. I've got x to the 4th, I've got x plus 2, all that divided by 2. There's what I'm taking the logarithm of. Okay, like I said, we'll have a few minutes. I'll probably make up another example or two of that just to give us a little more experience. But the last official thing that I have to say from this section is about what's called the change of base rule. So notice here's the calculator I bring to class. It's got a log button, that's my log base 10. It's got my ln, that's my natural log, my log base e, but it doesn't have the ability to take the log of any other base. Okay, so if I wanted to come up with some number values. So for instance, in example 6, I want to find out what's the value of log base 5 of 17, meaning 5 to what power? What's the power that I would raise 5 to in order to get 17? So what there is what's called the change of base rule. The change of base rule says that what I can do if I need to change the base is I can create a ratio. So what this says is for any positive real numbers, x, a, and b, where a is not equal to 1, a is the base of the original log, so a is the original base, and b is our new base. Then this is how you can change the base so that you could use your calculator, or if you were interested in using another base, you would say, okay, my new base is b. So in the numerator, I'm going to have log base b of what I was already taking the logarithm of, which is x. Then you're going to divide that by, in the bottom, you're going to take log base b of the old base, which is a. So whatever new base you're picking, like when we do example 6, I'm going to use base 10 because my calculator can do that. So I'm going to use base 10. So you take the log of your new base of what you were already taking the logarithm of. In this case, it's x. And then you take in the denominator log base b of the old base. So example 6, I want to calculate numerically, or I want to come up with an approximation of the log base 5 of 17. Okay, so here we go. I'm going to use the common log. You don't have to, but that's what I'm going to use. The answer would come out the same if you use the natural log, and if you want to compare on your calculator, it'll be the exact same thing. So here we go. So to use my calculator to figure out what this is, I'm going to have the common log, the log base 10 of what I was already taking the logarithm of, which is 17. Then I'm going to divide by, and my common log, my log base 10, my log of the old base, which is 5. So then I'm going to throw that down in my calculator. So here we go. Calculator, what is this? So I've got 17. I'm going to take the log of that, and I get that number right there. And then I'm going to divide by 5. I'm going to take the log of that, and that gives me 1.76 and a lot of other numbers. I'm just going to round to the 4th decimal place. So it's 1.7604 approximately. Let me make that an approximate. So I'd like you to do the same thing with exercise 13, the last one on that page. I want you to use your calculator. I'm going to use the common log just because I'm comfortable with it, but if you use the natural log, you'll come up with the same thing. What is an approximation of that? Round it to the 4th decimal place, please. Okay, so here's what I got. The way I'm going to do this ratio is I'm going to use the common log. So the log of 100, which is what I was taking the logarithm of originally, divided by the logarithm of my old base, which is 9. And what this is going to give me, remember my logarithm always produces a power. So this is going to tell me what power I raise 9 to in order to get exactly 100. Okay, 9 to what power is going to give me 100? Well, let's throw this in. So I've got 100. I'm going to take the log of that. Well, I get exactly 2. Then I'm going to divide by 9, the log of that, and it's going to be 2.0959. Well, let's verify that. I mean, I just told you that what that value should be is 9 to what power should be 100. Now we rounded, so it's going to be really close. So let's see. When I raise 9 to the 2.0959 power, it should come out really close to 100. Yeah, 99.999. That accounts for my round off error. And that's what the change of base rule gives you.